Hi everyone, welcome to the presentation for IETNet, abbreviated as Instance Explainable Temporal Network for Multivariate Time Series. Let's start with the outline. So we start with objectives, contribution, then move on to the model architecture, and then to the experiments with data evaluation metrics and results. Let's start with the overview. So here we use a multivariate time series data. So this is one of the real world recent NASA mission dataset used in this presentation. Real world data looks very noisy, and with all the regions of interest buried deep within the noise, there are also nonlinear interactions between multiple variables, and there can be like long-term and short-term dependencies in the data. So all this makes multivariate quite challenging. Objective is to develop a end-to-end network capable of ranking the importance of input variables of each instance. We have validated using multiple data sources, specifically a recent NASA mission sensor data. Our contribution is multifold. We have used shared temporal convolutional network to extract features. We have adapted transformer attention architecture to model the interactions between uh, various channels. We have also developed this novel channel gate to identify useful channels. We have developed all of this would be an end-to-end framework where it can be learnable. Uh, Moving on to the feature extractor, we have used a shared temporal convolutional network. The architecture is fully convolutional, thereby effectively reducing the number of parameters. So this is a huge problem in multivariate time series data. So over parameterization is a crucial problem. So we are sharing between all variables. The way we do this, the main component is dilated convolutions. So the dilated convolutions can exponentially increase the receptive field of the network. So here we stack multiple dilated convolution layers with the dilation factor increase of 2, thereby exponentially increasing the receptive field. Uh, After extracting we use ReLU activations and skip connections to make the network more stable. So after extracting the features, we use global pooling to collapse the time component of the features. So after that, we stack each variable into a matrix, as seen in the left corner here. So this matrix consists of 15 variables, and the x-axis would be the embedded dimension. Up to this point, there are no interactions between the variables. Now, to model the variable interactions, we use the attention layer. We use specifically the scale dot product attention. So what this equation does is it computes pairwise relationships between each variables. So here, Q, K, and V are query, key, and value. So the query and key are, we use the pairwise between each variable to obtain a pairwise matrix P, which has the relationships between interactions between each variables. So this after this block, we get the attention matrix between all of this. After that, to to weigh in the other variable interactions, we use the following equation here. M prime is the matrix that weighs in the interactions between all of the variables. Here, each variable is represented by Vj, and it's multiplied by the pairwise interactions between all of the variables. So we get the updated variable representation, which includes the interactions between all of the variables. So uh, till here, we get this M prime, which has the interactions between all the variables. Now, moving forward, coming to the most important part, we need to know which variables are useful for the classification. So we feed forward and collapse, feed forward and collapse and perform softmax to get this channel gate G. So the dimensions are basically number of variables by number of classes. Here, since it's a binary problem, we have one channel gate. For a multi-label problem, we'll have a channel gate for each of the label. So here, the sum of, after a softmax, the sum of channel gates would sum to 1. Here, red represents higher activation, blue represents lower activation, and white is the intermediate activation. So we try to get this channel gate, which forces the softmax would force to choose variables, and in a way, the channel gate channel gate represents which variables are important. So now using this channel gate, we gate the representation, the feature matrix M to get the final gated matrix. We do this using einsum. So you can, it's basically a matrix multiplication represented by the following equation. Here, B is the batch size, CH is the channels, F is the feature, and C is the classes. So we retain all the dimensions. Here again, we have only one gated matrix because it's a binary problem. If we have multiple multi-label problem, we have a gated matrix for each of the class. So now coming to the classification, we perform global average pooling to get the class score. So no other operation is performed after this part. So the class score is entirely dependent upon the channel gate. The, the channel gate is forced to pick right channels. If it doesn't pick right channels, the classification score would be bad. So in a way, when we perform gradient descent, the channel gate would learn in a way such that it needs to choose the right channels. So that's the whole idea in the paper. Uh, Now coming to the implementation part, we have the TCN, which has 16 filters, kernel size 2, along with following dilations. All variables share the same TCN. We have ReLUs for activation, Glora normal initialization, Atom optimizer with a cyclical learning rate, and a dropout of 0.5 is applied. Uh, Now for the evaluation, we use mean average precision at k retrieved objects. So here, the model would give which channels are useful, and we are trying to evaluate if there is correspondence between the retrieved channels and the ground truth channels. We do this by the following equation, which computes average precision at k. GTP is the ground truth positives, TP is the true positive seen, and I is the number of channels retrieved. Moving on to the data set. So this is a flux transfer event called an FT event. Here we have 15 variables. There are magnetic fields. The first 7 variables are magnetic fields in different dimensions. Then we have velocities. Then we have density and temperatures. So in an FTE, what happens is there is this peculiar bipolar event you can see in the blue variable. So there's this bipolar event happening and also corresponding patterns in BL and BX and some BMAG and in some density variables. So there is this interaction between different variables with the pattern repeating, and that's called an flux transfer event. We need to recognize this as a part of the problem. Um, for the results, so we can see IET net has an AUC of 0.84 in the data. So this we don't have much data. The overfitting is a huge problem here. So our efficient architecture has addressed that problem. We have outperformed LSTM by quite a bit. And then coming to the qualitative results, the model has picked BN, as you can see, and BX and some of the density parameters. So what we did is we took the average channel gate activations across all of the test set to get these results. And when there is no event, it doesn't look at the magnetic fields. And in the quantitative results, we plot the average precision at multiple Ks, and we have a significantly better performance. Uh, Coming to some of the discussion, so here we try to remove some of the useful channels. Let's say here we remove BN, and still the network picks the second most important channel, BX, BN being the most important informative channel. And here in the figure, we remove BX, the model picks BN. And when we remove both BN and BX, the model still picks some of the BMAG, mostly density. So it's still picking some of the important channels. In conclusion, we proposed a end-to-end classifier which provides important rankings of channels for each instance. We have effective parameter usage using convolutions and dot product attention. This can be a great utility in real world because most of the real world data is multivariate. Thank you. You can contact me at my email, and here is the code. Thanks.